A low hum vibrates through the fabric of space itself. It is not a sound you can hear, but a signal, a beacon from a monstrous heart beating in the dark. We are tuning into the supermassive black hole at the core of Centaurus A, our closest galactic neighbor hiding a cosmic secret. This is not just any black hole. It is a titan shrouded in dust, a relic of a catastrophic collision, and an engine of unimaginable power. By the end of this exploration, you will know 20 incredible secrets locked within this celestial beast, secrets that rewrite what we know about how galaxies live and die. Why does it fire jets of matter nearly 1,000,000 light-years long? What ghostly echoes of its past violence still linger today? The truth is stranger than any fiction. What do you think is the most shocking thing a black hole can do? That deep hum is the heartbeat of a hidden giant. Secret number 1, the colossal hidden monster. At the very center of Centaurus A, officially catalogued as NGC 5128, lies a gravitational anchor of almost incomprehensible weight. This black hole is not just large, it is a cosmic sovereign with a mass of roughly 55 million suns. To put that into a human scale, imagine compressing every star in our entire Milky Way galaxy down into a single point, and then doing it again with 54 million more galaxies just like it. That is the raw, concentrated gravity we are dealing with. But how do you weigh something you cannot see? Astronomers became cosmic detectives, using the world's most powerful telescopes to watch the stars trapped in its grip. Close to the galactic center, these stars are not placidly drifting. They are whipping around in a frantic, high-speed dance like moths caught in the vortex of a silent hurricane. By meticulously tracking their orbits, their speed, and their paths, scientists could calculate the immense mass needed at the center to hold them in such a violent waltz. The math revealed the monster. This leads us to the event horizon, the black hole's definitive boundary. It is not a solid surface, but a mathematical point of no return, a one-way door from which not even light can escape. For this particular titan, the event horizon would stretch across a space roughly as wide as the orbit of Mercury around our Sun. Picture that, an abyss of pure gravity, large enough to swallow our entire inner solar system whole, sitting silently at the heart of another galaxy. Yet for all its terrifying scale, this monster is a shy one. It is cloaked in a thick, ragged belt of cosmic dust and gas, the lingering debris from that ancient galactic collision. This shroud acts like a dense fog, blocking our direct view of the central engine in ordinary light. We must listen to its hum through other means, using X-ray eyes and radio ears to peer through the veil. This hidden nature is the first and most fundamental secret of Centaurus A, a reminder that the universe often conceals its most powerful forces in plain but dusty sight. That dark dust band is more than just a cosmic accessory. It is a scar, secret number 2, the relic of a galactic collision. To truly understand the beast at the center, we must rewind the cosmic clock by hundreds of millions of years. The majestic, peculiar shape of Centaurus A is not its original form. It is a ghost, a phantom image of a catastrophe frozen in time. The prevailing theory is one of cosmic violence on an almost unimaginable scale. Picture a calm, ancient elliptical galaxy, a vast cloud of old red stars. Now imagine a smaller, vibrant spiral galaxy, rich with gas, dust, and young blue stars drifting too close. Gravity, the universe's ultimate matchmaker and destroyer, took over. They did not simply pass by. They collided, they merged, they tore each other apart in a slow-motion dance of destruction that lasted eons. This was not a clean event. It was a chaotic, messy process that fundamentally reshaped everything. During this colossal merger, immense forces acted like a cosmic rake, violently stirring the galactic material. The delicate spiral structure of the smaller galaxy was shredded, But crucially, all that gas and dust it brought with it did not just vanish. It was funneled, driven by immense gravitational tides, directly toward the center of the newly forming hybrid galaxy. It was a feast delivered on a galactic scale, sent straight to the waiting mouth of the central black hole. This influx of fresh fuel is what likely awakened the dormant giant, igniting the powerful activity we see today. And that iconic, ragged dark lane that slices across Centaurus A, that is the direct evidence, the leftover debris from that ancient spiral galaxy. It is not a neat ring, but a warped, twisted belt of cold gas and dust, the final, sinking remnants of a galaxy that no longer exists as an independent entity. So when you look at an image of Centaurus A, you are not looking at a single galaxy. You are looking at a cosmic fossil, a snapshot of a merger still settling down. That dark dust band is a grave marker, and the active black hole it feeds is the roaring legacy of that long-ago violence. This collision set the stage for everything that followed, creating the uniquely chaotic and energetic environment that makes this black hole so extraordinary. This monstrous black hole does not just sit quietly in the dark. Secret number 3, a dual-personality beast. It is what astronomers call an active galactic nucleus, a technical term for a supermassive black hole that is actively feeding and, in doing so, unleashing tremendous energy. But Centaurus A's core is a unique hybrid, a cosmic chimera with a split identity. Its most famous and dramatic feature are its radio lobes. When we point radio telescopes at it, we do not see a point of light. We see two colossal, bubble-like structures erupting from the galaxy's core, stretching over 1 million light-years into the emptiness of intergalactic space. That is a distance 10 times wider than our entire Milky Way galaxy. These are not made of stars. They are vast clouds of ultra-energetic particles and magnetic fields, blasted out by the central engine and now slowly fading like the echo of a titanic scream. This incredible display makes Centaurus A the closest radio-loud active galaxy to Earth, a neighbor with a megaphone. Yet, if you look at it with optical telescopes, the kind that see visible light, the core appears strangely muted. It is not a blazing quasar, those unimaginably bright beacons that outshine entire galaxies. Its X-ray emissions, while strong, are also more restrained than some of its more ferocious cousins. This is the duality. It is simultaneously one of the most powerful radio sources in our sky, yet a relative underperformer in other wavelengths. Why this split personality? The answer likely lies in its diet and its dusty shroud. Scientists think it is feeding, but not at the frantic, chaotic rate that powers a brilliant quasar. It might be consuming material at a more moderate, steady pace, which is efficient at producing those focused jets and radio lobes, but does not generate the same all-encompassing inferno. That dark dust lane also plays a role, absorbing and hiding much of the higher energy light from our view. This very duality makes it a perfect cosmic laboratory. By studying this one object, astronomers can compare and contrast different modes of black hole activity, from the radio-loud outburst to the quieter feeding, all in our own galactic backyard. It is a reminder that these cosmic engines are not all the same. They have moods, modes, and personalities dictated by their environment and their last meal. Those colossal radio lobes are the ghostly footprints of a far more violent process. Secret number 4, the mysterious origin of its giant jets. To create structures that dwarf galaxies, you need a particle accelerator of almost unimaginable power. That is precisely what the black hole in Centaurus A has built. From its very poles, it fires twin beams of matter and energy, known as relativistic jets, directly into the void. The term relativistic is key here. It means these jets are composed of particles hurled outward at velocities frighteningly close to the speed of light itself. But how does a black hole, an object famous for sucking everything in, become the universe's most powerful blowtorch? The answer lies not in the black hole itself, but in the chaotic maelstrom just outside its point of no return. Picture the accretion disk, that swirling, superheated whirlpool of gas and dust spiraling toward oblivion. As this material is torn apart and compressed, it becomes an inferno of plasma, a soup of charged particles. Immense magnetic fields, woven through this chaos like strands of cosmic spaghetti, get twisted and amplified by the disk's insane rotation. These magnetic fields act as a cosmic railgun. They channel some of the doomed material not inward but outward along the axis of rotation, launching it in two narrow, focused beams perpendicular to the disk. It is a breathtaking escape act where a fraction of the energy from infalling matter is converted into a directional eruption of pure power. This is where the mystery deepens for Centaurus A. Many active black holes have jets, but few are as colossal, as persistent, and as incredibly well collimated as the ones we see here. Collimated means they stay tightly focused over immense distances, not spraying out like a garden hose but shooting like a laser beam for over 1,000,000 light-years. Why are these jets so exceptionally powerful and precise? Astronomers suspect it is a perfect and terrifying storm of conditions. The black hole's immense mass provides the gravitational anchor. Its moderate but steady feeding rate from the galactic collision debris might provide a stable fuel supply, and the geometry of its magnetic fields, shaped by the unique environment of the merger, could be acting as a perfect focusing lens. Within these jets, protons and electrons are whipped to energies billions of times greater than anything produced in our most powerful particle colliders on Earth. They are so energetic, in fact, that they are a prime suspect in one of astronomy's longest-standing puzzles. Some of the mysterious cosmic rays, high-energy particles that constantly rain down on our planet from deep space, are now thought to originate from jets just like these. So the next time you feel a subtle, unseen particle pass through you, it might be a silent messenger, a direct remnant from a jet fired 1,000,000 light-years away by the hidden heart of Centaurus A. But even those mighty jets are just the final product of a hidden furnace. Secret number 5, the enigmatic dusty torus. To understand the engine, we must look past the jets and peer into the very heart of the maelstrom, into the black hole's private chamber. Here, swirling just outside the point of no return, lies a structure so thick and dense it acts as a cosmic curtain. Astronomers call it the torus, a colossal, donut-shaped ring of gas and dust that encircles the black hole's equator, perpendicular to the jets. This is not a neat, smooth ring like Saturn's. Imagine instead a frenzied, chaotic storm cloud, a whirlwind of debris a few light-years across, so dense that it completely blocks our direct view of the brilliant accretion disk and the event horizon from most angles. It is the ultimate veil hiding the monster's face. This torus is the reason Centaurus A looks so different depending on how we observe it. In visible light, the torus is that dark, obscuring band. In infrared light, we can sense its heat, the glow of dust warmed by the hidden inferno. In X-rays, we can sometimes catch glimpses of radiation that manages to punch through or scatter around its edges. This very property of Centaurus A makes it a cornerstone for a revolutionary idea in astronomy, the unified model of active galactic nuclei. This model proposes a beautifully simple yet profound concept. Perhaps all supermassive black holes with accretion disks are fundamentally the same type of engine. Their wildly different appearances to us, from brilliant quasars to radio-loud galaxies like Centaurus A to seemingly quiet cores, might not be because they are different beasts. Instead, it might simply be a matter of perspective, of our viewing angle. If we look directly down the funnel of the torus with a clear view of the blazing accretion disk, we see a dazzling quasar. If we view it from the side, looking through the thick wall of the torus itself, the central light is blocked and we see something like Centaurus A, where the jets shooting out from the poles become the most prominent feature. Centaurus A, with its clear dust lane and powerful radio jets but obscured core, is the perfect middle ground example. it is like seeing a lighthouse from the side. You do not see the brilliant beam of the lamp itself, but you clearly see the powerful glow it projects out into the fog. By meticulously studying the size, density, and structure of this specific torus, astronomers are testing this unified model right in our cosmic neighborhood. They are learning how a simple twist of geometry, a mere tilt of a dusty donut in space, can completely change the face of a monster, making it appear as either a brilliant beacon or a shrouded enigma to distant observers like us. That dusty torus hides more than just the present. It conceals a violent past, secret number 6, a history of violent outbursts. This black hole has not been a quiet, steady engine. It is a cosmic volcano with a volatile temper, erupting in fits and starts that leave scars across its entire galaxy. The evidence is not in the brilliant jets we see today, but in faint, ghostly echoes. Using the sharp eyes of X-ray observatories and the sensitive ears of radio telescopes, astronomers have mapped the vast halo of gas surrounding Centaurus A. And there, embedded within that halo, they found something astonishing: giant, bubble-like structures. These are not the famous radio lobes. These are older, fainter, and much larger. They are colossal cavities carved out of the galactic atmosphere by unimaginably powerful blasts from the core in the distant past. Picture a pond after a large stone is thrown in. The initial splash is the current jet, but those expanding, faint ripples that reach the very edges of the pond, those are the fossilized outbursts. Each of these X-ray and radio bubbles represents a cataclysmic eruption that happened millions of years ago. The black hole, perhaps after gulping down a particularly large clump of debris from the galactic merger, would have entered a frenzied state. Its jets would have switched on with even greater ferocity than we see now, inflating these enormous bubbles of hot gas and energetic particles that slowly rose and expanded through the galaxy's halo. Then the feast would end, the jets would quiet, and the bubble would begin to slowly fade, leaving only a faint, cooler shell as a testament to the violence. By studying the size and distribution of these fossil bubbles, scientists can read the black hole's historical timeline. They suggest this monster has had multiple major eruptions, perhaps one every 10 or 20 million years. This paints a dramatically different picture than a placid, steadily humming engine. It is a portrait of a beast with a cyclical rage, one that sleeps, feeds, and then explodes with enough force to reshape its entire galactic environment. These outbursts are a crucial part of galactic ecology. They pump energy and heavy elements forged in the core's furnace out into the halo, heating the surrounding gas and preventing it from cooling and collapsing to form new stars. In a very real sense, these ancient temper tantrums help dictate how Centaurus evolved, showing that a black hole's influence is not a constant pressure, but a series of thunderous events that echo across cosmic time. Those ancient outbursts left their mark, but the current jet holds a puzzle of its own. Secret number 7, the curious case of the wobbling jet. When astronomers map the immense structure of Centaurus A's radio emission, they notice something strange, a subtle but undeniable misalignment. The inner part of the jet, the section closest to the black hole, does not point in exactly the same direction as the colossal, million light-year-long outer lobes. It is as if the nozzle of a fire hose was slowly, over millions of years, tracing a small circle in the sky, while the water it sprayed long ago froze into a fixed position. This phenomenon is called precession. Imagine a spinning top just as it begins to slow down, its axis tracing a wobbly cone. Now imagine that top is a supermassive black hole weighing 55 million suns. What could possibly cause such a titanic object to wobble? The leading theory points to a cosmic misalignment. Think of the black hole's spin axis as an imaginary pole running through its center. Now picture the accretion disk, that flat, swirling whirlpool of matter feeding it. In a simple, stable system, the disk would be perfectly perpendicular to the spin axis, like a record sitting flat on a turntable's spindle. But Centaurus A is not a simple system. It is the product of a violent merger, a chaotic environment where nothing is neat and orderly. It is possible that during the galactic collision, fresh gas and stars were funneled toward the black hole from a skewed angle. This new material could have formed an accretion disk that is tilted, warped, or even broken like a bent vinyl record. If the disk and the black hole's spin are not aligned, a dramatic tug-of-war begins. The immense gravity of the black hole tries to pull the inner parts of the disk into its own equatorial plane, a process called the Bardeen-Peterson effect. But the outer parts of the disk, carrying the angular momentum from the incoming material, resist. This internal struggle can warp the entire disk and, over time, cause the jet-launching region itself to slowly precess, to wobble, changing its aim by just a few degrees over vast timescales. Another possibility involves the black hole's own complex magnetic fields, which are twisted by the chaotic inflow of matter, creating forces that can torque and twist the jet base. Or perhaps the wobble is a sign of ongoing, smaller disturbances, the ghostly echoes of dwarf galaxies being swallowed long after the main merger, each one giving the system a slight gravitational nudge. This single, slight misalignment between the inner jet and the outer lobes is a tiny clue with enormous implications. It tells us that the environment immediately around this black hole is not in a state of calm equilibrium. It is a dynamic, unstable, and still settling place, a testament to the lasting chaos of its violent birth. The wobble is a silent record of that chaos, a slow-motion fingerprint of the forces that continue to shape the monster's heart. That slight wobble in the jet is a minor tremor compared to the raw power it unleashes. Secret number 8, a particle accelerator of cosmic proportions. Deep within those focused beams of matter, a natural and terrifyingly efficient engine is at work. The black hole in Centaurus A is not just a gravitational pit, it is the universe's most powerful particle collider, operating on a scale that humbles all human technology. Within its relativistic jets, protons and electrons are not simply being carried along. They are being violently accelerated to energies billions, even trillions, of times greater than what we can produce in our largest machines, like the Large Hadron Collider. How does it achieve this? The process is a multi-stage cosmic slingshot. It begins with the intense magnetic fields near the black hole, which give particles their initial, tremendous kick. But the real magic happens far out in the jet, where this high-speed flow eventually smashes into the slower-moving gas of intergalactic space. This collision creates immense shock waves, cosmic sonic booms traveling at near light speeds. As particles cross these shock fronts, they get caught in a turbulent back and forth, gaining a little more energy with each pass, like a surfer being repeatedly pushed by a wave until they are riding at an impossible velocity. This relentless process can whip a single proton to energies so high that it carries the kinetic force of a professionally thrown baseball, all packed into a subatomic particle smaller than an atom. These ultra-high-energy cosmic rays are so powerful they literally cannot be contained by our galaxy's magnetic fields, and they streak across the universe. For decades, the origin of the most energetic of these cosmic rays was one of astronomy's greatest mysteries. Centaurus A has now provided a crucial piece of the puzzle. Advanced telescopes have detected extremely high-energy gamma rays, the kind produced when these accelerated particles collide with light or other matter, streaming directly from its core and giant lobes. This was a smoking gun, confirming that such active galaxies are indeed factories for the universe's most energetic particles. But perhaps the most ghostly confirmation comes from beneath the ice of the South Pole. The Ice Cube Neutrino Observatory, a cubic kilometer of Antarctic ice instrumented with sensitive light detectors, has recorded neutrinos that trace a path back toward Centaurus A. Neutrinos are the universe's ghost particles, nearly massless entities that pass through planets and stars almost completely unimpeded. they are produced in the most violent environments, like the hearts of these particle-accelerating jets. To detect a neutrino that likely began its journey at the black hole in Centaurus is to receive a direct, unedited telegram from the engine itself, a signal that cuts through all the obscuring dust and gas. It is a new way of seeing, proving that the violence at the heart of this galaxy is not just a spectacle of light and radio waves, but a fundamental forge of the universe's most extreme matter and energy. Yet for all its immense power, this supermassive black hole did not form in isolation. Secret number 9, the mystery of the missing middleweights. To understand how a 55 million solar mass titan came to be, we must look beyond the galactic center to the ancient, glittering swarms of stars that orbit Centaurus A like distant satellites. These are globular clusters, dense balls of hundreds of thousands of stars, some of the oldest structures in the universe, and within them, astronomers are hunting for a crucial missing link: intermediate mass black holes. Imagine the black hole family. On one end, we have stellar mass black holes, the remnants of collapsed giant stars weighing perhaps 10 to 50 times our Sun. On the other, we have the supermassive monsters like the one at the heart of Centaurus A, weighing millions or billions of suns. The glaring question is, how do you get from one to the other? A stellar black hole cannot simply eat its way to supermassive size in the age of the universe. There must be a middle step, a seed. Intermediate mass black holes with masses ranging from a few hundred to a few 100,000 suns are the prime suspect. They could be the building blocks, the seeds that merged and grew through galactic collisions to become the giants we see today. This is where Centaurus A's rich collection of globular clusters becomes a cosmic treasure map. This galaxy is surrounded by a sprawling system of these ancient clusters, far more than orbit our own Milky Way. Each dense cluster is a potential cradle for an intermediate mass black hole. How would one form there? In the crowded core of a globular cluster, stars can collide and merge over billions of years. A particularly massive star could form and collapse, or multiple stellar black holes could themselves merge, gradually building up a heavier object. Finding one would be like discovering a missing chapter in the life story of every supermassive black hole. The hunt is on. Astronomers point their telescopes at these clusters, looking for subtle signs, the telltale swift motion of stars orbiting an unseen, massive object at a cluster's heart, or the occasional X-ray flare as a black hole tears apart a wandering star. While definitive proof within Centaurus A's clusters remains elusive, the galaxy's chaotic history makes it a perfect candidate. The same galactic merger that fed the central monster could have also funneled entire globular clusters and the black holes they might contain toward the center, providing the perfect building blocks for growth. So the search here is not just for one black hole, but for an entire hidden population, a potential family of middleweight monsters whose existence could solve the puzzle of how the central beast grew to such an unimaginable scale. The monster's appetite is as unpredictable as its temper. Secret number 10, feeding frenzy versus starvation diet. Right now, despite those colossal jets stretching across the cosmos, the black hole at the heart of Centaurus A might be on a surprisingly modest diet. Observations in X-ray and infrared light suggest it is in what astronomers call a low accretion state. The brilliant, searingly hot inner region of the accretion disk, the part closest to the event horizon, appears relatively faint. This means the whirlpool of matter spiraling inward is not a thick, raging river, but more of a thin, meandering stream. It is still enough to power the focused jets, but it is not the all-consuming inferno of a quasar. This presents a fascinating paradox. How can such a relatively underfed engine still produce such spectacularly large and energetic outbursts? The answer lies in efficiency. The jets themselves are a marvel of cosmic engineering, able to extract and focus a tremendous amount of energy from even a modest flow of infalling material, especially when channeled by those powerful magnetic fields. It is like a highly tuned motor that can produce impressive power even when it is not running at full throttle. But this quiet phase stands in stark contrast to the evidence of its past. Those fossilized X-ray bubbles and the sheer scale of the radiolobes are the undeniable leftovers of ancient feasts, periods when the black hole gorged itself on vast quantities of gas stirred up by the galactic merger. It has clearly experienced cycles of gluttony and restraint. This leads to one of the most profound secrets of all, a self-regulating feedback loop. Think of the black hole as a cosmic engine with a built-in thermostat. During a feeding frenzy, when gas floods inward, the engine revs to life. The accretion disk blazes and the jets switch on with immense force. But those very jets then blast outward, heating the surrounding galactic gas with their energy and pushing it away. This process, called feedback, effectively cleans out the black hole's own pantry. By violently expelling the fuel from its immediate vicinity, the jets starve the monster of its next meal. The frenzy ends, the engine quiets down, and the black hole enters a period of starvation. Over millions of years, gravity slowly pulls more gas back toward the center from the outer galaxy. The pantry refills and the cycle can begin anew. This boom and bust life cycle is crucial. Without this feedback, a supermassive black hole might consume everything in sight, growing uncontrollably and drastically altering its host galaxy. Instead, the energy it releases acts as a governor, regulating its own growth and in turn shaping the evolution of the entire galaxy around it. The relatively quiet core we see today in Centaurus A might simply be the calm after a storm, the monster resting after a colossal outburst, waiting for gravity to once again deliver its next cosmic meal to the doorstep of the abyss. This very proximity and power makes Centaurus A something far more valuable than a spectacle. Secret number 11, a laboratory for extreme gravity. Because it is the closest active supermassive black hole to Earth, its immense gravitational field offers scientists an unprecedented front-row seat to test the fundamental laws of the universe. Here, in the chaotic swirl of matter around a 55 million solar mass Titan, the predictions of Einstein's theory of general relativity are stretched to their limits. The goal is to move beyond simply observing the black hole's effects and to actually measure with exquisite precision how space and time warp in its presence. The most promising experiment involves watching the dance of doomed stars. Astronomers are using the world's most powerful telescopes, like the Very Large Telescope in Chile, to track individual stars that orbit perilously close to the event horizon. These are not the stars whipping around at a safe distance, but potential sacrificial probes sent diving into the deepest well of gravity we can see. According to general relativity, as a star completes each hairpin turn near the black hole, its orbit should not be a perfect, repeating ellipse like a planet around the sun. Instead, the orbit itself should rotate or precess, tracing a rosette pattern in space. This is due to the extreme curvature of space-time, an effect predicted over a century ago but never before measured so close to a black hole of this size. By tracking these stellar orbits over years, scientists hope to see this precession in action, a direct confirmation of Einstein's vision in a regime of gravity far stronger than our solar system. But the real prize will be finding a star that skims the very edge of a theoretical region called the ergosphere. This is the zone outside the event horizon of a spinning black hole where spacetime itself is not just curved, but is being dragged around the monster like a cosmic whirlpool. Nothing here can stand still, not even light. The very fabric of reality is forced to rotate with the black hole. If a star could be found orbiting within this maelstrom, its motion would show impossible signatures, moving in ways that defy all Newtonian physics and could only be explained by this frame-dragging effect. Observing it would be like seeing the ghost of the black hole's spin imprinted on the stars around it. Any tiny, unexplained deviation in these stellar paths could be even more revolutionary. It might hint at physics beyond Einstein, a crack in our understanding of gravity itself that only appears in the most extreme environments. Centaurus A, with its clear view and active core, is the perfect natural laboratory for this ultimate test. Every flicker of light from a star circling that abyss is a data point in humanity's greatest experiment, probing whether the rules that govern our reality hold true even at the edge of oblivion. The invisible rails guiding those jets are woven from pure magnetism. Secret 12, the magnetic field maze. While gravity creates the abyss, it is magnetism that truly tames the beast, transforming its destructive power into the universe's most focused blowtorch. The colossal jets erupting from Centaurus are not random sprays of matter. They are precision-engineered beams, and the blueprint for their construction is written in magnetic fields of unimaginable strength. But how do you map something invisible, a force that leaves no direct imprint on light? Astronomers become detectives of polarization. When light travels through a region dominated by magnetic fields, the electric and magnetic waves that make up that light get organized or polarized, aligning themselves with the direction of the magnetic field. By collecting the radio waves and X-rays from Centaurus A's jets and meticulously analyzing their polarization, scientists can trace the ghostly lines of magnetic force. It is like studying the patterns in iron filings around a magnet, but across 1,000,000 light years. What they have found is a labyrinth of staggering complexity. Close to the black hole, the magnetic fields are not simple straight lines. They are twisted into tight helices and braids, like cosmic ropes wound to the breaking point by the furious rotation of the accretion disk. This twisting stores immense energy, like winding up a rubber band. Farther out along the length of the jets, the fields often align into remarkably straight, parallel lines, forming the very rails that keep the particle beam focused over such incredible distances. The strength of these fields is almost beyond belief. They are millions of times stronger than the magnetic field that protects our entire planet. This magnetic maze does two critical jobs. First, it acts as a cosmic containment vessel. The charged particles in the jet, protons and electrons, are forced to spiral along these magnetic field lines. This prevents the jet from spraying out in all directions and keeps it collimated into those narrow, piercing beams. Second, and more profoundly, these fields are the engine's transmission. They are the mechanism that extracts energy directly from the black hole's spin, a process known as the Blandford-Zeenagic mechanism. Picture the spinning black hole dragging space-time around with it. The magnetic fields anchored in the accretion disk get caught in this drag, becoming twisted and wound up. This winding creates a tremendous voltage, like a cosmic battery, which then accelerates particles to near light speed and launches them outward along the rotation axis. The magnetic fields are not just shaping the jets, they are the very conduit that steals rotational energy from the monster and converts it into raw directional power. So when you see an image of those majestic million-light-year-long lobes, you are not just seeing matter, you are seeing the visible signature of an invisible magnetic architecture, a force so powerful it can channel the spin of a black hole into a beacon that shapes galaxies. The invisible magnetic rails that shape the jets also sculpt the galaxy in a more permanent way. Secret 13 echoes of the past in its stars. To read the deepest history of Centaurus A, we must look not at its dark dust or brilliant jets, but at the ancient light of its stars. When astronomers point their spectrographs at the chaotic heart of this galaxy, they perform a kind of cosmic archaeology, breaking starlight into rainbows to uncover its chemical composition and age. What they find is a stellar population in complete disarray, a clear record of multiple, violent chapters. Near the core, mixed in with the oldest stars from the original elliptical galaxy, are pockets of surprisingly young blue stars. These stellar infants are only a few million years old, a blink in cosmic time. Their presence so close to the gravitational monster is a profound puzzle. How can new stars be born in a place of such chaos and violence? The answer is a beautiful paradox. The same forces that can tear matter apart can also trigger its rebirth. During the colossal galactic merger, vast waves of gas were compressed and shocked, collapsing under their own gravity to ignite furious bursts of star formation. Later, the black hole's own outbursts contributed. Those powerful jets and the shock waves from ancient eruptions did not just destroy, they also created. As a jet plows into a dense cloud of galactic gas, it can act like a cosmic snowplow, shoving material into a compressed, dense shell at its leading edge. Within that shell, the increased pressure can become the very nursery for a new generation of stars. Imagine a powerful wind blowing across a pond, piling water into a wave. The wave crests and breaks, but within that turbulent motion, new structures form. So, some of the stars we see near the center may be direct children of the black hole's fury, born from gas crushed by its own energetic outflows. This creates a stellar tapestry of incredible complexity. You have ancient red stars from the galaxy's first generation, formed over 10 billion years ago. You have intermediate age stars from the merger epoch, a few billion years old. And you have these brilliant young blue stars, the newborns sparked by recent black hole activity. Their light is a layered timeline, a living archive that confirms the black hole is not just a passive destroyer at the galaxy's heart. It is an active, if violent, participant in the galactic life cycle. Its tantrums heat gas and suppress star formation across vast regions, but in localized, intense pockets. Its shock waves can also provide the decisive squeeze needed to spark stellar birth. The history of the monster is therefore written not just in empty bubbles and faint radio echoes, but in the very suns that now orbit it, each generation a silent witness to a different era of cosmic violence and creation. That stellar archive is a record of the past, but the black hole's signal is a constant in the present, a beacon that could one day guide travelers. Secret 14, a celestial lighthouse for navigation. This is a thought experiment, a leap into a speculative future, but it reveals something profound about the nature of this cosmic engine. For centuries, human sailors used the fixed, brilliant points of lighthouses to navigate treacherous coasts and open seas. In the unimaginable vastness of interstellar space, future explorers would need something similar, a fixed reference point that cuts through the dark. Centaurus A's jets provide a candidate unlike any other. Their colossal radio emission is not a flickering candle. It is a steady, brilliant hum that has persisted for millions of years and will likely continue for millions more. This makes it one of the most stable and recognizable landmarks in the entire local universe. You could compare it to a pulsar, the rapidly spinning corpse of a dead star that beams out regular radio pulses. Pulsars are indeed proposed as potential galactic GPS points, their precise rhythms acting like cosmic clocks, but Centaurus A's signal is different. It is not a rapid, ticking pulse. It is a broad, powerful broadcast, a constant roar rather than a metronome's tick. This could be an advantage. A pulsar's signal is a narrow beam, like a spinning lighthouse lamp, and you must be in the path of that beam to see it. The radio lobes of Centaurus A, however, are a sprawling, nearly omnidirectional structure. From almost any angle within millions of light years, a ship's sensors would pick up that distinctive, powerful signature. Think of it as a mountain range visible from any direction, rather than a single flashing light you have to be aligned with. For a civilization charting courses between stars, such a fixed, unmistakable landmark would be invaluable. By triangulating their position against this and other steady sources, like the quiet hum of the cosmic microwave background or distant quasars, navigational computers could plot a course with incredible precision. The central black hole itself, the engine of this beacon, would serve as the ultimate anchor point on the galactic map. Of course, this is a fanciful vision, but it serves a crucial purpose. It forces us to step back and appreciate the sheer scale and endurance of the phenomena we are studying. This is not a transient firework. It is a permanent feature of our cosmic neighborhood, a geological fact on a galactic scale. Its power and consistency across epochs is what makes such speculation possible. It transforms the black hole from a mere object of terror into a potential tool, a fixed star in a future sailor's sky, reminding us that even the most violent forces in nature can become, over enough time, a steady guide in the dark. That steady radio beacon is only one part of its spectral signature. A far more energetic ghost surrounds the entire galaxy. Secret 15, the ghostly gamma-ray halo. In recent years, orbiting observatories like the Fermi Gamma-Ray Space Telescope have unveiled a breathtaking new layer to this cosmic mystery. They have detected a faint, shimmering veil of gamma rays enveloping Centaurus A. This is not a pinpoint of light from the core or the bright knots in the jets. This is a vast, diffuse glow, a halo of the highest energy light in the universe, stretching far beyond the visible boundaries of the galaxy itself. Gamma rays are the ultimate product of extreme violence, produced when particles move at nearly the speed of light and smash into something else. But what is creating this immense ethereal shroud? The leading explanation is a haunting echo. It is the ghost of ancient cosmic rays finally meeting their end. For millions of years, the black hole's jets have been acting as that colossal particle accelerator, firing protons out into the darkness at nearly light speed. These protons, now cosmic rays, do not travel in straight lines. They become trapped by the galaxy's own sprawling magnetic field, spiraling along its invisible lines like cars on a cosmic freeway system. They can wander for eons, slowly diffusing through the galactic halo. Eventually, after a journey lasting millions of years, one of these ancient protons will collide with a lower energy photon of starlight or the cosmic microwave background, the faint afterglow of the Big Bang. This collision is catastrophic. It transforms the raw energy of motion into pure light, creating a gamma-ray photon. The faint halo we see is the combined glow of billions upon billions of these final explosive meetings. It is a delayed broadcast, a message from the past. The gamma rays we detect today were produced by cosmic rays that were likely accelerated during one of the black hole's ancient outbursts, long before the jets we currently see took their present shape. We are not seeing the black hole's present activity, but the lingering aftermath of its former fury, a fossilized energy field slowly fading away. This discovery changes how we see the galaxy's atmosphere. It reveals that the black hole's influence is not confined to the dramatic jets and lobes. It has permanently electrified the entire galactic environment, filling it with an invisible sea of high-energy particles that will take hundreds of millions of years to fully dissipate. The ghostly gamma-ray halo is a testament to endurance, proving that even a quiet monster leaves a radioactive fingerprint on its home, a signature of power that outlives the outbursts that created it. That ghostly halo is a signature of a single, powerful engine. But what if the engine itself has a hidden twin, Secret 16? Is it actually a binary black hole? One of the most tantalizing mysteries hanging over Centaurus is the possibility that its chaotic core does not house one monster but two. Think back to the galactic collision that created this hybrid galaxy. The smaller spiral galaxy that was devoured almost certainly had its own central black hole, likely a supermassive one. When galaxies merge, their black holes are expected to sink toward the new common center, drawn by gravity and friction with surrounding stars and gas. They begin a slow, gravitational dance, orbiting each other in a tightening spiral that can last for hundreds of millions of years. Theoretically, Centaurus A should be the perfect place to find such a cosmic duel. So, where is the second black hole? The search is on, but it is a hunt for a shadow within a shadow. Direct observation is nearly impossible with current technology. Two supermassive black holes in a close orbit would appear as a single, blurry point of light and energy even to our best telescopes. Astronomers must look for indirect clues, subtle fingerprints in the data. One clue is asymmetry. The motions of gas and stars very close to the core might show a strange, lopsided pattern, a gravitational tug of war that cannot be explained by a single point of mass. It would be like seeing a whirlpool with two drains, creating a complex, unstable flow. Another clue would be a periodic signal. As the two black holes whip around each other, their immense gravity could cause regular flickers in the brightness of the accretion disk or create a wobble in the jet that repeats over a predictable time frame. Finding such a rhythm would be a smoking gun, yet despite careful searching, definitive proof remains elusive. The challenges are immense. The black holes could be so close together that their orbital period is just a few years, making the signal hard to distinguish from normal turbulence. Or they could be in a wide, lazy orbit that takes thousands of years to complete, meaning we have only observed a tiny fraction of their dance. They might also be in a stalled state, having spiraled into within a few light years of each other, and then run out of surrounding stars to steal momentum from, leaving them trapped in a seemingly eternal embrace. The presence of a second black hole would solve several puzzles. It could help explain the precession, the wobble of the main jet, as the gravitational pull of a companion constantly perturbs the disk. It could also account for some of the unusual structures and bursts of star formation right at the galactic center, stirred up by the gravitational chaos of two titans circling each other. For now, the binary black hole in Centaurus A remains a compelling ghost, a theory born from its violent history that has yet to step fully into the light. Its potential existence transforms the core from a single abyss into a ballroom for giants, a silent, slow-motion duel happening in the dark, whose outcome will one day shake the galaxy with gravitational waves. The possibility of a hidden twin makes the monster at the heart of Centaurus A seem even more unique. Yet its true nature is revealed not in its solitude but in its contrast. Secret 17, the secret of its silent neighbors. Look up at the night sky toward the constellation Sagittarius. There, hidden behind thick clouds of dust, lies our own galactic center, anchored by a supermassive black hole named Sagittarius A star. In many ways, it is a sibling to the beast in Centaurus A. Their masses are surprisingly comparable, both weighing in at several million times the mass of our Sun. But their personalities could not be more different. Ours is a sleeping giant, a quiet gravitational pit that only occasionally burps after swallowing a small cloud of gas or a stray star. Centaurus A's black hole, on the other hand, is a roaring engine with million light-year-long jets. Why such a dramatic difference? The answer is not in the monsters themselves, but in their pantries. A black hole is only as active as the food it can reach. Our Milky Way is in a relatively settled, mature phase of life. It has not undergone a major merger in billions of years. The galactic center is relatively clean, with only a trickle of gas and the occasional star wandering too close. Sagittarius A star is on a starvation diet, and so it slumbers. Centaurus A is the polar opposite. It is a galaxy still recovering from a catastrophic collision. That ancient merger did more than just warp its shape. It delivered an unimaginable banquet of fresh gas and dust directly to the central black hole's doorstep. Think of it like two dormant volcanoes. One sits in a calm, eroded landscape with no magma source. The other has just had the entire landscape ripped open by an earthquake, flooding its chamber with molten rock. The first is quiet, the second erupts with terrifying force. This is the core secret of black hole activity. The monster does not decide to be loud or quiet. Its behavior is a direct reflection of its cosmic environment and its violent history. The fuel supply dictates everything. Without a steady influx of matter to heat into a brilliant accretion disk, even a 55 million solar mass Titan appears dark and silent. With a feast, it becomes a lighthouse. This comparison teaches us a humbling lesson about our own place in the cosmos. The quiet at the heart of our Milky Way is not the norm, it is a fortunate calm. We orbit a sleeping dragon. Centaurus A shows us what happens when the dragon wakes, fed by the chaos of a galactic collision. Our peaceful spiral is the exception, a temporary quiet in a universe where such monstrous engines are often ignited by violence. Our own quiet galactic center is a cosmic anomaly, Secret 18, a window into the early universe. To understand the dawn of galaxies, we must look not only outward into the deep past, but also next door at the raging heart of Centaurus A. This nearby monster is more than a spectacle, it is a time machine. In the chaotic infancy of the cosmos, the universe was a very different place. Galaxies were smaller, gas was abundant, and titanic collisions were the rule, not the exception. Supermassive black holes were not sleeping giants. They were frequently awakened, gorging on the plentiful debris of these violent mergers and blazing as brilliant quasars. That frenzied epoch shaped everything we see today, but it is incredibly difficult to study directly. The most distant ancient galaxies appear as faint, blurry smudges of light, their details lost to unimaginable distance. This is where Centaurus A becomes our greatest guide. It is a rare, nearby replica of those ancient conditions. Here, we have a front row seat to a galaxy still reeling from a major merger, with a black hole actively feeding and driving colossal jets. We can see the structures in exquisite detail, measure the temperatures, map the magnetic fields, and trace the flows of gas with a clarity impossible for those faraway primordial galaxies. By meticulously dissecting this local example, astronomers are building a master blueprint, a detailed model of how black hole feedback works. They can see exactly how the jet energy heats the surrounding gas, how it drives powerful winds, and how those processes suppress star formation across vast regions. This blueprint is then applied backward in time. When a telescope captures a faint, reddened glow from a galaxy 10 billion light-years away, scientists can now ask informed questions. They can estimate the power of its hidden black hole, not just from its light, but by understanding the relationship between jet power, radio lobe size, and the heating of galactic gas they have mapped in Centaurus A. It is like having a perfectly preserved engine from a vintage car. By taking it apart and understanding every component, you can then look at a blurry photograph of a similar car from a century ago and know exactly how it must have worked, how powerful it was, and how it shaped the roads of its time. Centaurus A is that pristine engine. Its roars and whispers are giving us the vocabulary to translate the faint signals from the ancient cosmos. Through this local monster, we are learning that the furious black holes of the early universe were not just ornaments. They were the master architects, using their violent feedback to regulate the growth of their host galaxies and ultimately forge the structured universe we inhabit today. The blueprint of galactic evolution is still missing its most fundamental component, Secret 19, the unseen influence on dark matter. We have traced how this black hole shapes stars, gas, and light, but its greatest impact might be on something we cannot see at all. Dark matter, the invisible, mysterious substance that makes up over 85% of the matter in the universe, forms a vast, ghostly halo around every galaxy, including Centaurus A. It is the hidden skeleton upon which the visible galaxy is built, and at the heart of that skeleton, where the black hole sits, something strange might be happening. This ventures into the most speculative realm of cosmology, where theory meets the edge of our understanding. Some models suggest that a supermassive black hole, with its incredible density, could act like a gravitational anchor within the dark matter halo. As dark matter particles, whatever they are, stream through the galaxy, they could be pulled and focused by the black hole's gravity, creating an ultra-dense spike in the dark matter distribution right at the galactic center. Think of it like a rock in a stream. The water, representing the dark matter halo, flows around it, but directly behind the rock, the water becomes more turbulent and concentrated. The black hole could be creating a similar, invisible wake of concentrated dark matter. This leads to an even more extraordinary possibility: annihilation. If dark matter particles are their own antimatter counterparts, a concept in some theories, then where they are densely packed together in this spike, they could collide and annihilate each other, converting their mass into a burst of gamma rays or other exotic particles. It would be a silent, invisible fireworks show happening in the absolute dark, powered by the mutual destruction of the universe's most elusive substance. This is where Centaurus A becomes more than a laboratory, it becomes a hunting ground. Its active, massive black hole and our clear view of its core make it a prime candidate to search for these theoretical signals. Astronomers are scouring the gamma-ray and X-ray data from its center, looking for an unexplained excess of high-energy radiation that cannot be accounted for by the jets or the accretion disk alone. They are searching for the faint, predictable signature of dark matter dying in the monster's grip. So far, no definitive signal has been found, but the search itself transforms our understanding of the black hole's role. It is no longer just an engine of visible creation and destruction. It is a potential probe, a natural instrument that could be illuminating the properties of dark matter simply by existing. Its gravity might be sculpting the invisible universe in ways we are only beginning to theorize. This secret connects the most powerful visible object we can study to the greatest invisible mystery in the cosmos, suggesting that to solve one, we may need to listen very carefully to the other. Every secret we have uncovered, from its violent birth to its ghostly gamma-ray halo, is a single frame in a movie that spans billions of years. Secret 20, the future fate of a cosmic titan. The monster at the heart of Centaurus A will not rage forever in isolation. Its destiny is already written in the slow, gravitational choreography of our local universe. Look ahead beyond millions, beyond even billions of years. Our Milky Way, Andromeda, and Centaurus A are not static islands. They are all moving, drawn together by their immense mutual gravity in a slow cosmic dance. In roughly 4.5 billion years, our galaxy will collide with the Andromeda Galaxy, beginning a merger that will mirror the ancient crash that created Centaurus A. Over eons, this new hybrid galaxy, often called Milkomda, will settle. But the dance does not end there. Our entire local group of galaxies, including the now distant shape of Centaurus A, will continue to fall inward, pulled by the combined gravity of the merged Titan. In time, perhaps tens of billions of years from now, Centaurus A itself will be drawn into the fray. Its own journey will come full circle. The black hole born from one merger will face another. As the galaxies intertwine for a second time, their central black holes, each a monster weighing tens of millions of suns, will begin their own fatal waltz. They will spiral toward each other, stealing momentum from stars flung violently away, until they are locked in a final, intimate orbit. Then, in a flash of energy that will briefly outshine every star in the new supergalaxy, they will collide. The resulting gravitational waves will ripple across the cosmos, a final shout announcing the birth of a new, unimaginable Leviathan, a single supermassive black hole with the combined mass of over 100 million suns. This is the ultimate secret, the final chapter written in gravity. The chaotic, brilliant life of Centaurus A's black hole is not an end, it is a middle act. It is a seed for something even greater in a future so distant that all stars we now see will have long since died. Our local cosmic drama, from the quiet of our Milky Way to the radio roar next door, is just one thread in an infinite tapestry of collision and rebirth. The monster we study today is both a relic of the past and a blueprint for the future, a reminder that in the life of the universe, even titans are temporary, destined to merge and become part of something new in the endless dark. From a single, monstrous heartbeat in the dark, we have traced 20 layers of a cosmic enigma. The black hole at the heart of Centaurus A is far more than a simple destroyer. It is a complex, living engine, a sculptor of its galaxy, a particle accelerator of staggering power, and a natural laboratory pushing the limits of physics itself. We have seen how its violent birth in a galactic collision set the stage for everything that followed, fueling the jets that stretch 1,000,000 light-years and the ghostly gamma-ray halo that surrounds it. We have watched it cycle between quiet restraint and explosive outbursts, regulating its own growth and the evolution of its entire home. It challenges our understanding of gravity, hides the potential ghosts of dark matter, and may even hold a hidden twin in a slow-motion duel. This single object, our closest active supermassive neighbor, ties together the grandest stories of the cosmos, from the chaotic mergers of the early universe to the silent dance that will one day pull our own galaxy into its future. It reminds us that the most terrifying forces in nature are also the most creative, the most enduring, and the most instructive. If you ever find yourself under the clear skies of the southern hemisphere, look toward the constellation Centaurus. There, invisible to your eye but humming with radio waves and X-rays, lies this magnificent engine. Which of its 20 secrets did you find the most astonishing? Was it the wobbling jet, the ghostly particle echoes, or the possibility of a hidden binary monster? Let us know in the comments below. And if you want to join us as we unravel more mysteries of the cosmos, from black holes to the birth of stars, be sure to subscribe. The universe is full of stories waiting to be told, and the next one is just a click away.